Right, let's start. So let's briefly review what we studied the last time. Okay, so given a square matrix A, we multiply some invariable matrix P on the right and then its inverse on the left, and then if we can change this matrix A into diagonal matrix D, then we call it as a diagonalization, right? So here in order to perform this diagonalization, we need this invariable P, right? And then also we can if there exists such a diagonalization equation, and then we can change it into this form by just multiplying P over here and P inverse over here, and then we will obtain this A is equal to PD P inverse, and we call it as eigen decomposition, which is a particular form of a matrix factorization of a square matrix A, right, into these three pieces. And all three matrices P and D and P inverse, they are all square matrix. So A is square and PD, P inverse are all square matrix. But here P is invariable matrix and also D is diagonal matrix. If we can find such a P and D, and then if we can find this kind of equation that is equal to A, and then we call it as a eigen decomposition, right? And then these two are equivalent one, diagonalization and also eigen decomposition, right? But here we studied about the requirement of the columns of P and the diagonal elements of D. So given this diagonalization equation, we can just multiply P over here, and it is equal to AP is equal to PD. And if we call this column of P as V1, V2, and V3, and then AP, which is this part, this AP is represented in this form, right? The resulting matrix in this column is A times V1 and A times V2 and so on. And then in the case of PD, so P still has the same column of an V1, V2, V3, and our matrix D is assumed to be diagonal matrix over here. And so let's call this diagonal elements of this matrix D as lambda 1, lambda 2, and lambda 3. And then we studied, we understood that it's a column-wise scaling. So the first column times lambda 1, the second column times lambda 2, and the third column times lambda 3. And so here AP should be equal to PD, and so this AV1 should be equal to lambda 1 V1, and AV2 should be equal to lambda 2 V2, right? And so we obtain this kind of equation, which is exactly the same as the eigenvalue and eigenvector kind of equation. So in conclusion, the columns of P should be eigenvector, and the diagonal elements of D should be eigenvalue in its corresponding column, right? And so there should be no other vectors other than this eigenvectors. So if we fill out some other columns, then eigenvectors in this column of P, and then we cannot perform this diagonalization at all. Okay. And also here we examined this equation of AP is equal to PD, and so we were able to move from the left to the right with no problem. But in order to go back from the right to the left, we need the matrix P being invariable, and so P should be square matrix, and also linearly P has to have linearly independent columns to be invariable, in order to be invariable. And so if we can find only like 2 eigenvectors, and then still, I mean, given this a 3 by 3 matrix, if we can find only the two linearly independent eigenvectors, or just 2 eigenvectors, and then let's form this a P as 3 by 2, right? As 3 by 2 by just choosing 2 eigenvectors that we know. Okay, and in this case, even if P is not a square matrix, AP and this P times D, where D is formed as 2 by 2 diagonal matrix. And in this case, we can just remove this part, and then we can still see that AP is equal to PD, right? So here we need, in the case of 3 by 3 matrix A, we need 3 linearly independent columns to form the square matrix, and its columns should be linearly independent. And so in order to have this diagonalization, in order to make this diagonalization possible, we need n linearly independent eigenvectors to form the square matrix P as an invariable matrix, right? And so how can we make, or when can we obtain n linearly independent eigenvectors? Okay, so that was the question that we studied. And so back to this guy. Okay, so we consider this algebraic multiplicity and the geometric multiplicity given distinct eigenvalues, right? So by the fact that they have these algebraic multiplicity, we know that this characteristic equation is lambda 1 to the power of 3, lambda 2 squared, lambda minus 4 to the power of 5, right? And so for each lambda, 1, 2, and 4, we know its corresponding eigenspaces are linearly independent, right? But for each eigenvalues and their corresponding eigenspaces, the linearly independent, or the basis for this eigenspace, is at least 1, right? At least 1, because those eigenvalues will make the matrix A non-invariable. So the A minus lambda I times X is equal to 0. This kind of homogeneous linear system will have non-trivial solution, right? And so it means the eigenspace, or the null space of A minus lambda I, is at least 1. The dimension of this subspace is at least 1. But even though we didn't prove it, but we studied that the maximum number of dimensions, or maximum dimension of each eigenspace, is like bounded by this algebraic multiplicity, right? So the dimension of the eigenspace is called the geometric multiplicity, and this geometric multiplicity is less than or equal to its corresponding algebraic multiplicity, right? And so in this case of like 10 by 10 matrix, so it's a 10 by 10 matrix, and that's why we have the sum of these algebraic multiplicity as 10, assuming that we have all the real values as our solution for this 10th order polynomial, or 10th order equation. Okay, so if we have complex solution or non-real solution as something like in the case of 3 by 3 lambda, I think I showed this example. So lambda squared minus lambda plus 5, and in this case we have one real root, or one real solution for this equation, but we have 2 complex numbers as our solution. In this case, this matrix will, this matrix cannot be diagonalizable. It is not diagonalizable because our algebraic multiplicity for the real root, which is 3, is 1, right? So at most we can find only one linearly independent basis for our eigenspace for this guy, for this guy, for complex root or complex eigenvalue. We consider them as we just ignore them, or we exclude them as our possible eigenvalues, right? So we only consider the real values. So in this case, there is no way to achieve the three linearly independent eigenvectors, right? So over here, only when or only if we can achieve this geometric multiplicity as the maximum possible value, which is the same as algebraic multiplicity, and that's when we can have 10 linearly independent eigenvectors. Okay, so that way we can diagonalize the given matrix. Right? Any questions so far? Okay, then let's go back to the chapter 5.3 and so let's look at this example. So it could be one of your exam kind of problem, because that is a typical kind of exercise problem that you will see in the book. So we have an A here, and so the question is to diagonalize this matrix. And so it's a matter of finding out 3 linearly independent eigenvectors as well as their eigenvalues. So we first form characteristic polynomial a minus lambda I, and then form the characteristic equation, and then find out the root of this characteristic equation in this form. And then for each of them, so in the case of an algebraic multiplicity and geometric multiplicity, so lambda being 1 and -2, and so this is 1 and this is 2, because this number is coming from over here. Okay, so we know it is at least 1, right? But this guy is upper bounded by 1, so it will only have one free variable in the case of a minus lambda I. So in the case of lambda being 1, then it will be 0, -6, -6, and 0, right? So if we do the Gaussian elimination, it will only have one free variable, and thus the dimensionality of this dimension of this null space of an a minus lambda I is 1, and so we will find one eigenvector. And then in this case, so this is the one that should be carefully checked. So in the case of lambda being -2, there will be like 3 and -3 and 3, right? So in this case, we perform the Gaussian elimination to form echelon form, and then if it has only one free variable, and then it means our geometric multiplicity over here is 1. So in this case, this matrix is not diagonalizable, right? So once we found this kind of pattern, and then we can just stop and then complete like the answer of this problem as, okay, this matrix is not diagonalizable. That's it. And if we can find this geometric multiplicity for this lambda as 2, which corresponds to like two free variable, and then this means this matrix is diagonalizable, right? And then we can find lambda and its corresponding eigenvector for each of lambda being 1, lambda being -2. Okay, and then we will have a 3 linearly independent vector, one from here, one from here, and 2 from here. And then we know that the eigenvectors between these two. Eigenspaces of the distinct or different eigenvalues will be always linearly independent, right? So that was quite important theorem that we studied, right? So there was, in the this guy, right? This theorem 2, eigenvalues are different and their corresponding eigenspaces will have no overlap, or any eigenvectors coming from different eigenvalues will be always linearly independent, right? So between these two, the eigenvectors between these two different eigenspaces will be always linearly independent. Okay, and that way we can form our P, which is whose column is our eigenvectors, right? And then we can also form our D as the corresponding eigenvalues. Okay, so these two are the basis vectors, and you guys know the reason why reason we see over here 1 0 and 0 1, because they are corresponding to the free variable in our homogeneous linear system. They are parametric vector form. You know how to factorize the free variable and then obtain this constant vector that will form our basis. They will work as our basis vector for the null space. So P is obtained in this manner, and D is obtained over here. Okay, and then we can verify that they are, AD is equal to, it's typo, right? AP is equal to PD. Okay, so that's how we diagonalize a given matrix. Okay, it's almost a review of what we already studied. Okay, and then now let's move to the next chapter. But we will go to the lecture material that I additionally uploaded in the other day. 이거 있죠? 이 파일? Okay, so this time we will study the linear transformation of using A, which is AX. Okay, so here let's assume A is diagonalizable, or the eigendecomposition A exists as it's a PD P inverse, or so I just used V instead of P. Okay, and then this VD V inverse times X is our linear transformation. Okay, and then here we can see this kind of transformation defined by the matrix A as like 3 steps of a linear transformation, where X is first linearly transformed by by using the matrix V inverse, and then suppose the resulting vector as Y, and then this Y is further transformed by the matrix D, and then maybe that result, let's call that result as C, and this C is further transformed by V, right? So these kind of 3 steps of a linear transformation should be the same as the linear transformation defined by a single matrix A, right? Then here let's look at each step in these 3 steps of a linear transformation. Okay, so what is this V inverse times X? Okay, so here, yeah, for example, suppose A is 2 by 2. Okay, A is 2 by 2. So the two-dimensional vector is transformed into the two-dimensional vector. I mean, domain and the codomain are just two-dimensional space. And then this A has the eigenvector and eigenvalue as -1 and V1. Okay, V1 is something like this, 3, 1, for example. Okay, and also A has another eigenvector and eigenvalue as V2 and its corresponding eigenvalue as 2. Okay, so let's assume this kind of situation. And then here, what's the meaning of this transformation V inverse times X? So let's call this S on Y and this, right? And we know V is a square and also invariable matrix, as we see already, V inverse in this form. And so it can be written as Vy is equal to X, right? So X is 4, 3, right? And then we now represent this 4, 3 as the linear combination of our eigenvectors, right? So V1 is maybe 3, 1 over here, and V2 is -2, 1. Okay, by looking at this this point over here. Okay, and so yeah, computing Y or obtaining Y is, yeah, given this original like two-dimensional input vector, and then we represent it as a linear combination of 3, 1 and -1, 2 and 1 times maybe Y1 and Y2, right? And then also you guys know that this is a representing the given vector X as a linear combination of these two eigenvectors, right? And these two eigenvectors are linearly independent, right? And then in the two-dimensional space, how many eigenvectors, how many linearly independent eigenvectors do we have? 2, right? And so those eigenvectors, okay, will span the entire two-dimensional space. Or in general, if we have n linearly independent eigenvectors, and then given the any n-dimensional vector, okay, and then we can represent it as a linear combination of our n linearly independent eigenvectors. And how many solutions do we have? So they are linearly independent vectors. So the solution is always unique, right? And so in this particular case of two-dimensional space, we have two linearly independent eigenvectors. And so these two linear combination coefficients of y1 and y2, yeah, will be uniquely obtained. Okay, right. And then in this case, geometrically, yeah, we want to represent this x as as the vertex of this parallelogram, where the two line segments are stretched by V1 and V2, right? And so by looking at this kind of grid and the parallelogram pattern, it seems to be like V1 times 2 and V1 times 1, right? So it will be, yeah, y1 and y2 will be 2, 1. Okay, or in general, this guy is 2 times V1 and 1 times V2. So we basically represented a given input vector as the linear combination of eigenvectors, and those two are the linear combination coefficient or weights. Okay. And then yeah, let me give a high-level overview of this kind of transformation. Okay, so yeah, once representing X as the linear combination of our eigenvectors, okay, and then yeah, let's think of this AX, which is the linear transformation defined by the matrix A, okay, and then yeah, this guy is X is represented in this form as a linear combination of eigenvectors, right? And then yeah, first performing linear combination and then applying the linear transformation defined by A will be the same as we first perform the linear transformation on these two given matrices, and then later on we linearly combine them. Those two will be the same, right? But here, the reason why we represent the input vector as a linear combination of eigenvectors is because this part and this part will be easily computed by utilizing this scalar multiple of the input vector. Okay, and so 2 times and 1 times, and so 2 lambda 1 times v1 plus 1 lambda 2 times v2. Okay, so that's the beauty of utilizing these eigenvalue and eigenvectors. Okay, so here yeah, so suppose A is 2653, although this is not a correct one in this example, but yeah, let's suppose A times X. Okay, so in this case we have to perform this inner product over here and this inner product over here to form the final result. Okay, but instead of performing this kind of computation, we actually represent this guy as 2 times v1, like this guy, and then what is v1? v1 is 3,1 and v2 is negative 2,1, and their corresponding eigenvalues are negative 1 and 2, right? And so 3,1 times, originally we had a 2 as a linear combination coefficient to represent the input vector x, but while performing the linear transformation with an a given this eigenvector, then it is just simply represented as a scalar multiple of this eigenvector. So the eigenvalue is negative 1. So simply, instead of computing the matrix A over here, we just simply replace this as this with just a scalar multiple, right? And so negative 2 over here. Okay, and then negative 2 and 1, and its corresponding eigenvalue is 2, and we have 1, which is original original linear combination coefficient while representing the matrix x, the input vector x in terms of an eigenvector, right? And so that's it. And so negative 2 and 2 and 3 1 plus negative 2 1, and so negative 6 and negative 2, negative 4 2, so 0 and negative 10. Okay, so we can perform, or we can compute this linear transformation of this 4, 3 in this manner. Okay, so at a high level we want to perform this kind of linear transformation by utilizing eigenvectors and their corresponding eigenvalues by avoiding the actual matrix multiplication. Okay, so in order to do so, I mean, this process is viewed as like these kind of 3 steps of these 3. Okay, so we will see a little bit more details on why or how this process is equivalent. I mean, these two are equivalent. Okay, so back to this example. I mean, we understand this y, okay, as a linear combination when using the basis as a eigenvector, okay, and representing our input vector by using these eigenvectors, okay. And also, this is called the change of basis. And why is it called this change of basis? It is because, yeah, so originally 3, 4, I mean 4, 3 is the coordinates when our basis is 1, 0 and 0, 1, or standard basis vector, right? And then now this guy is the same as 2, 1 when our basis vector, yeah, maybe b prime as 3, 1 and negative 2, 1. Okay, so you guys can understand this. So we still consider the same point, exact same point of, yeah, this point. This point is fixed. I mean, the location is fixed or position is fixed. But when using, I mean, when representing that point by using the standard basis vector of 1, 0 and 0, 1, and then this one is the coordinate vector. Okay, but yeah, when using or when representing that as by using the new basis of eigenvectors, and then their coordinate will be now changed into these two values, right? So this is the meaning of the first transformation of v1 v inverse times x. Okay, we now represent the same point as the new coordinates when using our basis vectors as eigenvectors. Okay, does it make sense? Right, and then when we obtained these two coordinates with respect to the eigenvectors as our basis, okay, and then multiplying the matrix A over here will be just a matter of just the scalar multiple of this guy times lambda 1 and this guy times lambda 2, right? So that guy, I mean that scaling, I mean dimension-wise or element-wise scaling is done in the second transformation of D. So what is D? D is diagonal matrix where this guy is a lambda 1 and this guy is lambda 2, right? And so this is the same vector x. Yeah. Yeah, sorry. I actually wrote in a wrong manner. So this guy is not true. So in terms of the notation, it is still 4, 3, right? But this guy, no, it is right. It is right, right? So this is the coordinate vector that we studied, right? And I think it's consistent or is correct. Yeah. Okay, and then this guy is y actually. 2, 1 is our y, and then 2, 1 is multiplied with our diagonal matrix, right? But here, yeah, typically we will perform this inner product between these two to obtain this guy and this guy and this guy and this guy, right? But here, by the fact that our matrix D is diagonal matrix, okay? In the case of diagonal matrix, we can just simply perform the element-wise scaling, right? So it's even though it looks like the matrix times vector or D times Y, but it is not really the matrix multiplication. It's just a scalar multiple, okay, in the corresponding elements. Okay, and then yeah, and then the next step or the third step. Yeah, once performing this dimensionalized scaling in terms of this new coordinate where our basis is eigenvectors, okay, and then it is a matter of dimensionalized scaling by the factor of eigenvalues for each axis, okay, and then we now reconstruct it into the standard basis, okay. So here this is done by this matrix V, and the V is, yeah, I mean V has the columns of an eigenvectors, okay, that's it. And so here this dy, or this 2 times -1 is lambda 1, and this is lambda 2, okay. So that way we obtain these, but these are the coordinates with respect to b prime, where b prime has the basis of 3, 1 and -2, 1, which are the 2 eigenvectors, okay. And then we want to represent it as just a vector that corresponds to the standard basis, okay. So in that case, so we obtain the -2 and 2 as these result, -2 and 2 over here, and then V is composed of the eigenvectors as the 2 columns, right? And then once just multiplying V with this coordinate values or coordinates with respect to our eigenvectors, right? And then it's just a linear combination of these 2 columns, right? And these V1 and V2, or these are 3, 1 and -2, 1, these are the vectors with respect to the standard basis 1, 0 and 0, 1, right? And this is also 1, 0 and 0, 1, okay. And so we represent this kind of representation for V1 and V2 with respect to these standard basis, and then just multiply their corresponding coefficient or coordinate values, and then just obtaining the result is the final vector that we obtain as -10 and 0, and this is the coordinate vector as 1, 0 and 0, 1, okay. So once obtaining these 2 coordinates, and then we have this V2 times 2 and V1 times -2, and then we actually reconstruct this point as the standard basis of 1, 0 and 0. So this is the final or the third step. Okay, so at a high level we represented the input vector x, and this it's a linear transformation which is called the tx, right? It's ax, and then we changed this coordinate with respect to the new basis, where the bases are the eigenvectors, right? And then in this space the linear transformation with an A is just nothing but the diagonal scaling or element-wise scaling, okay, of each dimension. So that's how we obtain the C, and then we go back to the original coordinate system where we use the standard basis vectors. Okay. Any questions so far? 네.
그러면 이런 디컴포지션을 하는 이유가
네.
아무래도 컴퓨테이셔널 에피션시 때문이 될 것 같은데.
네.
그렇다면 만약에 A가 그냥 A 제곱, A 3제곱 이런 멀티플이 아니라 그냥 단순히 A인 경우에만 봤을 때는 비효율적인 과정이 되지 않나 싶어가지고, 그럼 뭐 A 제곱, A 3제곱 때문에
네.
그런 제곱에 대한 연산은 D에서는 그냥
네.
D제곱, D3제곱
네.
단순한 연산이 되니까
네.
똑같지만 그냥 A가 그냥 A, 그리고 D도 그냥 D면 그렇게 된 경우에는 이제 뭐
네.
비효율적인 연산이 되지 않을까 싶어가지고.
네. 그러니까 이제 이거 하나만 이제 이 a랑 곱하는 거 이거 한 번만을 하기 위해서 이렇게 세 단계로 하는 게 뭐 오히려 더 복잡한 것처럼 나는 보인다. 이거 하려면 아이겐 벡터랑 아이겐 밸류 다 구해야 되고 캐릭터리스틱 이퀘이션 다 풀어야 되고 그 널 스페이스 a 램다 i도 다 구해야 되고 그게 훨씬 더 페인풀한 거 아니냐. 그것도 맞는데 이게 그러니까 계산상의 이피션시만으로 이걸 하진 않고요. 이거에는 훨씬 더 뭔가 좀 심오하고 굉장히 유용한 여러 가지가 좀 있어요. 그래서 이게 일단은 우리가 매트릭스를 이제 리니어 트랜스포메이션이라는 것은 이렇게 있으면 기본적으로 첫 번째 디멘전은 EX1 플러스 6X2 그 다음에 5X1 플러스 3X2 이렇게 정의가 되죠. 그렇죠? 여기서 이 그러니까 아웃풋으로 나오는 첫 번째 디멘전은 우리한테 주어져 있는 인풋 디멘전 모두를 다 뒤섞어서 뭔가를 만들어요. 역시 두 번째 디멘전도 모두를 다 뒤섞어서 이렇게 만들잖아요. 네. 그리고 저게 하여튼 저게 뭐 또 아이겐 벡터나 밸류는 방향이 안 바뀌고 이제 스케일링만 된다. 근데 이제 일반적으로 여기에 뭐 2653에 뭐 1, 2 이렇게 놓으면 뭐 방향도 바뀌고 크기도 바뀌는 벡터가 나오잖아요. 그게 이제 저 두 개의 디멘전들을 뭔가 서로 이제 뒤섞는 과정 때문에 이제 뭔가 일어나는 현상인데 이렇게 되면은 뭔가 좀 생각하기가 약간 골아프잖아요. 뭐 네, 골아픈데 이게 만약에 세상이 좀 심플하게 이 x1에 무조건 상수배만 되는 거죠. 3x1 얘의 상수배 마이너스 2x2 뭔가 우리의 이제 선형 변환이 디멘전별로 서로 섞지 않고 각 디멘전에 있는 값들의 그냥 상수배만 이렇게 곱해주는 이런 형태의 이제 변환이라면 뭐 얼마나 좋을까 혹은 이제 얼마나 뭔가 세상이 좀 심플해지겠나 하는 거죠. 네, 그래서 이게 약간 네, 그렇게 어떤 일단은 행렬을 통한 이제 선형 변환, 그러니까 행렬을 곱해서 이렇게 만들어지는 변화는 이렇게 서로 디멘전을 이렇게 뒤섞는 과정에서 이게 뭐가 어떻게 되는지 좀 잘 직관적으로 잘 파악이 안 돼요. 근데 이게 약간은 change of basis, 그러니까 우리가 베이시스를 일단은 같은 점인데도 불구하고 베이시스를 그냥 아이겐 벡터들로 이루어지는 베이시스 벡터로 네, 우리의 좌표 평면이든 좌표 공간을 나타내고 나면 거기서는 그냥 이런 식의 디멘전별로만 이렇게 스케일링이 일어날 뿐이라는 거예요. 그러면 이 경우는 이제 어떻게 되냐면 약간 이런 거거든요. 그러니까 이게 원래 뭐 4,3이 이렇게 있다. 그러면 이 벡터의 선형 변화는 물론 이렇게 또 생각을 해볼 수 있어요. 그러니까 1, 0, 0, 1. 그 다음엔 이 1, 0, 그러니까 2차원에서 2차원으로 간다. 그러면 이 1, 0, 그러니까 스탠다드 매트릭스 우리가 배웠듯이 얘는 예를 들면 1로 가요. 얘는 뭐 예를 들면 뭐 1로 갔다 쳐요. 그러면 여기에 이제 원래 4배니까 여기 이제 하나 둘 셋 네 개 해갖고 이렇게 가는 거죠. 그리고 얘는 하나 둘 세 배니까 얘가 또 하나 둘 세 배 해갖고 이렇게 가서 요게 변환의 아웃풋인 거잖아요. 맞죠? 이게 우리가 스탠다드 매트릭스를 배웠을 때 이제 리니어 트랜스포메이션에서 배웠던 뭐 그런 거잖아요. 네. 근데 이제 이게 또 어떻게 볼 수 있냐면 이 똑같은 벡터가 예를 들면 아이겐 벡터로 분해를 했을 때는 여기 표현서 보면 어떻게 그리는 거죠? 아 그렇지 이렇게 그리는 게 아니라 점선을 많이 찍었네. 자 이렇게 그래서 자 요 같은 벡터를 예를 들면 여기까지가 v1이에요. 그래서 요만큼은 2v1이고 네, 여기는 하나 둘 세 개 해갖고 여기까지가 v2고 여기는 이제 잘못 그렸네. 얘가 아니라 얘죠. 하나 둘 셋 해갖고 여기까지가 v2고 그 다음엔 여기가 이제 3v2죠. 그러니까 같은 점을 이렇게 분해를 해놓고 나면 자, V1에 대한 이제 아이겐 밸류가 만약에 뭐 3이다. 얘는 3이고 램다 1은 3이고 얘에 대해서의 램다 2는 4다. 그럼 이게 광활한 스페이스가 있네요. 아직 이거를 네, 요거에다가 결국 이 방향으로는 이게 하여튼 2v1이잖아요. 우리 인풋 벡터 x를 가지는. 그랬을 때 이거를 이렇게 3배로 늘리는 거죠. 여기. 그쵸? 그 다음엔 역시 이것도 이게 내 4라 그랬나요? 네, 4면 멀리 가야 되네요. 아, 네. 하여튼 여기가 하나, 둘, 셋, 4배 여기라고 하면 자, 이렇게 되면 여기가 하여튼 아웃풋이 된다는 거거든요. 아니, 물론 이 아웃풋이랑 여기랑 똑같진 않지만 지금 이게 정확하게 매칭이 되게 그리진 않았으니까. 그러니까 지금 보면 축을 우리가 이렇게 초록색으로 이루어지는 아이겐 벡터들로 우리의 좌표 공간에 있는 점들을 나타내면 그러면 매트릭스 멀티플리케이션은 그냥 이 축으로 해당하는 배수, 이 축으로 해당하는 배수. 그 다음엔 이렇게 된다는 거예요. 그러니까 평행사변형의 모양 자체는 어떻게 보면 혹은 이제 축은 입력단이나 출력단이나 그 축 자체가 변화하지는 않는다는 의미가 돼요. 근데 여기서는 아까 봤던 것처럼 1령, 0일 이 두 개의 축이 이 축 자체가 회전을 하잖아요. 회전을. 그러니까 회전이라는 게 축의 방향이 이제 바뀌잖아요. 그러니까 아까 내가 요 1령이 여기로 간다 그랬나요? 그쵸 아마? 예. 그 다음에 뭐 이 0일은 또 여기로 내가 간다 그랬나요? 예. 이렇게 뭔가 우리가 갖고 있던 어떤 그 벡터드 그러니까 그 스탠다드 베이시스에 해당하는 그 벡터의 이제 방향 이제 그 코디네이트 시스템을 나타내는 그 베이시스 벡터가 그거 하나하나가 다 이렇게 우리가 이제 매트릭스 A를 통한 선형 변화를 하면 그 벡터들의 방향도 바뀌고 크기도 바뀐다. 그러니까 걔네들의 어떤 또 똑같은 선형 결합의 가중치에 의한 조합으로 만들어지지만 그러니까 이 축이 이렇게 뭔가 바뀌는 게 축의 방향이 바뀌는 거가 우리는 좀 복잡하잖아요. 그러니까 저 복잡한 게 어떻게 보면은 아이겐 벡터로 우리의 축을 나타내면 그 방향은 이제 더 이상 바뀌지 않고 그 축별로만 스케일링만 이루어지는 거라고 생각을 하면 좀 더 쉽다는 거죠. 자, 그 다음엔 이게 뭐 그때 얘기했던 뭐 파워 메서드라는 걸 이야기를 했는지 모르겠는데 파워 메서드 이야기했나요? A를 이제 여러 번 곱한다. AX가 아니라 A 백승의 X 뭐 이런 걸 한다 보면 했나요 이거? 네. 이것도 역시 마찬가지로 이것도 이제 뭐 보면은 네, 하여튼 까만색 이 라인으로 하여튼 어떤 점이 있을 때 하여튼 이 까만색의 좌표계로 뭔가 이 점은 예를 들면 뭐 대충 뭐 이렇게 나타내시겠죠. 그러면 여기가 이 아이겐 벡터 축 베이시스 벡터로의 어떤 좌표계가 생길 텐데 근데 중요한 건 이쪽 성분은 지금 4배씩 늘어나고 이쪽 성분은 지금 3배씩 늘어나고 그러면 그 그러니까 방향은 그대로 그때 저쪽은 이제 4의 백승 이쪽은 3의 백승 이렇게 되잖아요. 그러니까 결국은 그거 두 개를 다시 합치면 결국은 저쪽 방향으로의 벡터만이 형성이 되는 거죠. 그러니까 방향성만 따지면 그러니까 이쪽 성분보다 훨씬 더 긴 거잖아요. 4의 백승이 3의 백승보다 훨씬 크니까. 네, 그러니까 이제 저 방향 성분으로 거의 눕는 형태로 저 방향에 이제 거의 붙는 형태로 이제 벡터 방향 성분이 결정이 되게 되는 거죠. 하여튼 그렇고요. 네, 또 다른 질문 있나요? Right, so yeah, viewing the linear transformation defined by the matrix A as this simple dimension-wise or element-wise scaling is really important, and this gives a kind of effective perspective of easily understanding this matrix multiplication. Okay, and also, yeah, if we have a eigenvalue as 4 and eigenvalue as 3, and then when multiplying the matrix A over and over, and then this larger eigenvalue and its corresponding component will be more and more dominant in terms of the resulting vector direction. Okay? And then also, in this case, yeah, suppose we have, we deal with the 3 by 3 matrix, and then we have 3 different eigenvalues and its corresponding eigenvectors. I mean, 3 linearly independent eigenvectors, and their corresponding linear eigenvalues are 3 and 2 and maybe 1. Okay, so in this case, along this axis, the coordinate will be 4 times bigger, and along this axis, the coordinate will be just 1 times larger than the original one, right? So in this case, as we saw, as we keep multiplying A, the eigenvector corresponding to largest eigenvalue will be more and more dominant. And so in this case, suppose this guy became, 4 to the power of 100. It became like 10 to the 16th, and then this guy will remain as 1, and so 1 and 10 to the power of 16. So in this case, this number 10 to the power of 16, so that is kind of magic number, so that is called the machine precision. Your computer is precise up to that amount, only to that amount, or in other words, your machine cannot distinguish between these two, and the difference between these two will be like this guy, right? But your computer cannot compute this large gap of numbers and their computations. So in this case, computers cannot distinguish between these two, and then even if we perform this computation, then computer will just give us 10 to the power of 16. So simply, it will ignore this part. And this is because we have the finite we use the finite bits to represent a single number. So when using computer, 1/3 cannot be exactly or accurately represented. It is impossible to represent this number fully accurately, because it is like 0.333, right? And it's infinite, right? But our computer uses a finite or fixed length of bits to represent a single number. So it should be chopped off at a certain point, right? So this is a similar case. So even if we just add it over here, then it cannot be represented, or it cannot be distinguished, or it cannot be accurately computed. Okay, so it will be just considered as 10 to the power of 16. Okay, so this is called the machine precision. So in this case, if the smallest eigenvalue and the largest eigenvalues and their gap, or more exactly, their ratio. So suppose smallest eigenvalues are 2, and the largest eigenvalues are maybe 30. Okay, and then if this kind of ratio is larger, if this ratio is large, and then in general, your computer becomes more and more inaccurate. Does it make sense? Because as you multiply A over and over, and then it will reach easily to the level of a gap between the 10 to the power of 16 and 1. Okay, in terms of the ratio. Okay, and so in this case, your computer will become quickly inaccurate. Okay, and in the case of a deep learning is just a matter. It's just a sequence of linear transformation. Okay, so deep learning looks like this. So In the case of deep learning, input vector is a 5-dimensional vector. And in the first layer, it is just a linear transformation from R5 into R6. Okay? So we have a linear transformation matrix A defined over here. And over here, we apply the second step of a linear transformation where the input is 6-dimensional and the output is 7-dimensional. Okay, in this case, we have our own matrix B over here, which is a 7x6. Okay, and so here, even though we do not multiply this matrix over and over, but we multiply matrix A over here and also multiply B over here and so on, right? And so, it can also be viewed as like a little bit of the process of becoming more and more inaccurate in terms of your output vector due to the finite representation of your computers for an arbitrary number. So in that case, it will be beneficial, or it will be generally better to have the small gap between the smallest eigenvalue and the largest eigenvalue for this matrix and this matrix and so on. Okay, so so in general, this smallest eigenvalue and the largest eigenvalue of a given matrix A. Okay, this is called the condition number of a given matrix. Condition number. And so, if it is as small as possible, and then your matrix will be kind of more friendly to your potentially inaccurate computers. Okay, but if this guy is really big, and then your computers is potentially becoming inaccurate much more quickly, and so that will impact or degrade the deep learning accuracy or performance or the training speed and so on. And so so there is so this is a kind of an advanced technique called a spectral normalization. So this is an advanced deep learning kind of additional regularization technique where these gaps to be small as possible when training or when optimizing the linear transformation matrix defined at each layer. Okay. But anyways, so other than this computational efficiency issues, eigenvectors and eigenvalues are kind of debunking or making a little bit complicated linear transformation process into much more simpler form, which is just a dimensionalized scaling. Okay, so that is the point. And this eigen decomposition, and also it's an extension to a little more general kind of rectangular matrix case called the singular value decomposition. So we have a very, very similar matrix decomposition called the singular value decomposition, defined for any general rectangular matrix, not just for square matrix. Okay, so that is called the singular value decomposition, and these two techniques or these two matrix decompositions are really playing a lot of role in the many different applications. It's a ton of applications or use cases. Any other questions? Okay, then let's take a 10-minute break, then resume at 1:10.
이게 지수생일 때문에 저기 P 인버스 2에 그뭐 n승 P 하면 되니까 빨라지는 걸 알겠는데 그럼 빨라지는 걸 이해하겠는데 당연히 근데 산화일 때도 뭔가 장점이 있다는 얘기를 아직 설명하신 게 뭔 소리인지 이해 못했어요. 그러니까 그냥 약간 지금 축을 먼저 틀고 나서 계산하는 거죠. 그러니까 근데 아까 전에 뭔가 얘기를 하죠. 뭔가 이득이 왜 이득이 되는지 모르겠어요. 그걸 이해했어요. 뭔가 많이 큰 계산을 하면 한쪽으로 계산하기 쉬워진다는 정도 이해했거든요. 빨리 결정해진다지. 그러면은 이 기능을 처음에 저게 제일 방법이 있다는 걸 특별한 이렇게 할 때 여러 개의 단행을 여러 개 분해하는 걸 할 수 있다는 이 용어를 줄여서 계산을 정확하게 할 수 있다. 아마 다른 저는 준영원이에요. 힘내라고. 저는 분명히 준영원이었습니다. 저는 아직 정혜원이 아닙니다. 생각해보면 저는 아직 준영원이에요. 나 이거 저 분명히 준영원이거든요. 뭐라고 했나? 근데 끝나겠다. 뭐야? 지금 준영은 자꾸 이런 거 되는지 모르겠어요. 증명이 써 있어 저게. 맞아 이거 떼어놓은 팔이야. 네 이거 11년은 버전만 10인데 이거이냐? 이거는 반말이야. 이거 여기 프로필이다. 11호이다. 자명하다. 이거 좀 그래? 선대 된다고? 이거 보면은 첫 번째 그냥 걸어가서 그리고 있는데 말하는 느낌만 있고 근데 이게 엑서가 해주는 게 모르면 이게 다 같이 됐던 것 같아요. 이게 똑같네요 하는 그런 왠지 모르겠는데 그냥 내보세요 할까요? 이게 이렇게 하니까 이게 되네요 이거 왠지 알겠 이거 왠지요. 보통 알지. 이거 왜 이건지 외우고 다녀? 이게 뭐야? 이거 약간 우리가 한 별씩 외우고 다니는 것처럼 약간 그거잖아. U 내점 U 맞고 내 Y 내점
또 증명 가능해요. 증명할 때 증명이라고 하면 지금 문제를 풀 때 증명하는 모든 공식에 대한 증명.
그런 거지. 한 별씩 외우고 다니는 것처럼.
증명을 열심히 해.
완벽하게 얘기한 말이야. 아니 몰라 호비에 10만 원 아닌가? 네? 에스페 10만 원이야. 우리 잘못안 나더라고. 20만 원. 생각보다 비싸요. 이 생각보다 이 타블렛이 되게 비싸. 야, 아깝다.
이걸로 쓰면
그러니까 20만 원. 써도 아무거나 되네. 쓰세요. 하나 똑같은 방식으로 써도 똑같은 방식으로 되신다고. 상위 기준에서 하위 기준을
그 하시는 말씀이 그냥 AX로 하면 축을 돌려야 되는데 만약에 이런 식으로 그냥 바로 그 아이겐을 이용하면은 돌릴 필요 없이 그냥 아이겐 벡터의 몇 배만 해서 이렇게 더하면은 이게 축 돌릴 필요 없이 값이 나와서 좀 더 효율적이다 이 말씀이신 거예요?
네. 이렇게 볼 수 있고, 네, 그 하여튼 뭐 효율적이라는 의미는 좀 아주 효율적인 상황이 있는데 이제 그렇기보다는 하여튼 그 어떤 축을 딱 그 아이겐 벡터를 우리의 베이시스로 하면 그 축 자체는 전혀 회전이나 그러니까 방향이 바뀌지 않은 채 그 축만으로의 스케일링으로 이제 A라는 변환을 AX라는 변환을 생각할 수 있다.
근데 그것도 결국 축을 돌리는 거 아니에요? 아이겐 베이시스로.
네, 원래 값을 그러니까 스탠다드 베이시스에서 표현되던 값들을 아이겐 벡터의 베이시스로 나타내어지는 그 코디네이트로 바꿔야 되는 거죠.
네, 근데 AX도 축을 돌리기 때문에 약간 조금 뭐랄까 그게 복잡해서 아이겐 베이시스를 쓴다고 하셨는데 그럼 아이겐 베이시스도 결국에 축을 돌리는 건데
네.
똑같은 거 아닌가요?
그 사실 우리가 아이겐 베이시스, 아이겐 벡터를 우리의 베이시스로 한다면 그럼 사실 우리는 그 좌표계에서 그냥 머물러도 사실 되는 거거든요. 그러니까 굳이 스탠다드 베이시스로 나타내어지는 좌표계로 이렇게 돌아올 필요는 없는 거죠, 사실. 네, 그러니까 꼭 그러니까 그쪽 스페이스를 그 새로운 어떤 우리의 축을 그 아이겐 벡터들로 이루어지는 축 혹은 베이시스로 하는 뭐 거기서 이제 계속 머무른다고 하면 뭐 어떤 점을 나타내는 그 코디네이트이 있을 거고요. 그 아이겐 벡터들로 이루어지는 베이시스에 대해서. 거기서는 A라는 매트릭스에 의한 변화는 그냥 그 축에서의 디멘전별로의 스케일링이다라는.
좀 생각을 해봐야 될 것 같아요. 일단 한번 생각을 해볼게요.
네, 그래요. Right, let's continue. Okay, so we know how to diagonalize the matrix, right? And then in the last part of this chapter 5.3, there is a theorem 6, and this theorem is saying that this theorem is about some special case of what we already studied. So we are given a square matrix, n by n square matrix, and let's imagine it's a characteristic equation, and suppose it has all n distinct eigenvalues, which means given maybe 3 by 3 matrix, and then we have lambda minus 2, lambda plus 1, and lambda minus 4, and all the algebraic multiplicities are 1s. So we consider this kind of situation. So that way we have three distinct or three different eigenvalues, right? Because nth order polynomial or equation has an n distinct solution or root, and it means our algebraic multiplicity should be all ones, right? So in this case, yeah, if we imagine this kind of table, -1, 2, and 4 as our lambda and algebraic multiplicity and geometric multiplicity, and algebraic multiplicity is all ones, right? And then the geometric multiplicity should be at least 1 and also at most 1, right? So this is an upper bound, but we know it's at least 1. So the only possible way is that the geometric multiplicity is 1 for each eigenvalue. So in this case, if we sum them up, and then yeah, we can always obtain 3 linearly independent eigenvectors, right? So we don't need to worry about like strictly smaller geometric multiplicity than algebraic multiplicity, right? So if it is a 2, and then we should worry about like whether geometric multiplicity for this case is 1 or 2, and if it is 1, which is a strictly smaller than 2, in that case, this is the case that this matrix is not diagonalizable, right? But in the case of algebraic multiplicity being all ones, and in that case, we don't need to worry about this kind of situation. And so, n by n matrix with an n distinct eigenvalues is always diagonalizable. Okay? And again, between different eigenspaces, yeah, we know they are automatically linearly independent, right? So each of these 3 vectors from 3 different eigenvalues will be linearly independent. Okay. And then the next theorem, or theorem 7, is what I already described. So this is about the algebraic multiplicity being smaller than or equal to geometric multiplicity is smaller than or equal to algebraic multiplicity. Any questions? Okay, and that's it for eigenvalues and eigenvectors. And we have several more chapters in chapter 5. Okay, yeah. And yeah, we will move to the chapter 5.4. And this is almost what we already studied in terms of this guy, like these 3 steps. Okay, but we discussed a more general kind of situation, and there, general form of a mathematical notations and so on. And from now on, it's actually my first time to teach this chapter. So it might be a little bit sloppy. So in that case, please ask questions or do your own self-study. Okay. Right. So it's all about the change of basis, or this coordinate changes that we already studied, but we studied in the context of a linear transformation. Okay, so suppose we are like 2-dimensional space as a domain and the 3-dimensional space as a codomain, and in the 2-dimensional space as a particular subspace called a V, we can think of our domain as not the entire 2-dimensional space, but a general kind of subspace V, which is a part of R2. Okay, and also W, which is our range. Okay, range is belonging to R3. Okay, So in this case, given this subspace and any particular point, and then let's imagine some particular basis to form our subspace V. So yeah, so in this case, so let's just make or assume this V is the same as R2, the entire two-dimensional space. And then yeah, we can easily think of several different basis vectors. For example, 1, 0, and 0, 1 is one kind of basis vector to form our subspace V, or maybe 2, 1, maybe 1, negative 2. This is another basis vector, right? And so we can think of a particular basis vector B. And now let's think of this X, which is originally represented as maybe, yeah, this standard basis vector, okay? And then we can consider this guy as the new coordinate with respect to a new basis vector. For example, like this guy and so on, okay? So we have this new coordinate with respect to the new basis B. And then now we can also think of another basis vector to form our range, okay, our range. Okay, in that case, we can also consider some basis vector to form our range, and then for any function output or any linear transformation output, yeah, originally it was represented as maybe 1, 2, 3, for example, but in this case, we can also imagine it's a coordinate vector with respect to the new basis vector C, okay, that forms our subspace W, right? And then we have new representation which is of an input vector with respect to the basis vector B, and the new representation of an output vector corresponding to this input vector, okay, Tx, represented as a new basis vector C, okay? And then can we define the new linear transformation that maps this guy into this guy, okay? So as a special case in this situation, I mean, let's imagine this this kind of situation, okay? So here, so our domain and the codomain was R2 and R2, right? And then let's imagine the basis vector, I mean new basis vector B, which is eigenvectors, okay? And then there was like a 3, 3 was represented as 2, 1, right? So that is like this guy, 2, 1, B. And now in this particular case, so this is our range or codomain, but here let's also imagine, I mean, let's assume we use the same basis vector B over here, okay? And in this case, 2, 1 was changed into what? 2, 1 was changed into negative 2, 2 by applying this diagonal scaling or element-wise scaling, right? And then now by using these two coordinates with respect to eigenbases, and then we reconstructed them into this vector where B is standard basis, right? But if we just stay in this representation and the output representation of negative 2 and 2, so that was our eigenvector, right? Multiplying with the negative 1 and 2, okay? So this is still like B, okay? And in this case, yeah, we have this input vector and output vector represented with respect to eigenvectors, okay? So in this case, we can now define our linear transformation linear transformation matrix as D, right? So we originally had an A over here. Let's say it was 2653. Okay, so this representation is when our input and output vectors are represented with respect to the standard basis vector, right? But here, when representing input and output vector as those coordinate vector with respect to the new basis vector b and also b, for example, and in this case, we can also imagine its corresponding linear transformation matrix D over here. And the characteristic or main kind of property of this matrix D was that it was a kind of simple diagonal matrix, right? So that's the kind of beauty of changing our basis and their corresponding coordinate systems, right? So we studied this kind of situation in a more general kind of form. So we can now have a different dimensional kind of domain and codomains, right? And also their kind of subspace, and then their own basis vector b corresponding to the domain, and the c, which is another basis vector corresponding to the range. Okay, so we consider this kind of situation, and then let's think of this. Let's get familiar with this kind of representation. This guy is like 2, 1, okay, and 3, 1, negative 2, 1, right? And this was, this representation was 4, 3. I keep writing it, this equation, but we understand this guy. It's this guy, right? And then now, what is this Tx? Tx is the, for example, some three-dimensional vector, this Tx is originally like this kind of this kind of output vector, but when using it with respect to the coordinate, the basis c, and then it will have its own kind of coordinate vector, right? So now this Tx, you can conceptually understand this Tx as this fixed point, okay? But this fixed point is represented with respect to the basis of C, okay? Then what is the corresponding linear combination coefficient? And that linear combination coefficient will be put or will be placed over here, okay? So let's familiarize this kind of notations. All right, then let's just evaluate this relationship. So this xb, suppose this xb is represented in this form, and then this guy is like r1 times b1 and r2 times b2 and so on, right? So here this guy is 4 times 1, 0 and 3 times 0, 1, and this guy 2 times 3, 1 and 1 times negative 2, 1. Okay, so this linear combination is represented in this form. So that is viewed as reconstructing this vector in terms of the standard basis, right? Okay, so x is represented in terms of the new basis, and then let's apply the linear transformation t, and then due to this linearity, so we can apply first linear transformation, and then later on we can form linear combination as well. And then in this case, we can also represent this guy in terms of like tb1 and tb2 and so on as a kind of standard matrix, okay, times r1 and rn, which is the coordinate with respect to the basis p, okay? But here let's think of this kind of output vector, or this guy is represented in the standard basis, right? This guy is represented as a standard basis because B1 and Bn, all of them are represented as the coordinate vector with respect to the standard basis, right? So it's like reconstructing this guy, 2 times 3 comma 1 and 1 comma negative 2 times 1. So reconstructing them into some vector, it is represented as a standard basis, right? And then applying this linear transformation T, so this representation is still represented as a standard basis in our codomain. And then now let's represent it with respect to the new basis C. Okay, new basis C. So this is the same point like this guy, okay, this guy, and then representing it as this new coordinate system C is now represented over here. So R1 times this guy, and this guy is still represented, this guy is a vector represented with respect to the standard basis. And now let's represent that vector with respect to the C, basis vector C, okay? And then, this is the coordinate vector represented with respect to the basis C and C. So here, what we applied was, so this is an output vector with respect to the standard basis in the codomain. And now, this is a 1 point, and then let's think of their new coordinate vector representation of this new coordinate vector, new coordinate basis C. Okay, and then this coordinate is actually also the linear transformation. Okay, so even though we don't prove it, but you should be able to easily prove that. Okay, so like so this guy is changed into this form, right? And also we have 5, 6 is represented as maybe 3, 2 with respect to this B over here, okay? And in this case, this guy plus this guy, or maybe 9, 9 is represented as the summation of these two, right? Okay, so this coordinate operation is also applied individually to each of an output. Okay, so later on we form the linear combination of these outputs. Okay, so conceptually, so it is as follows. So x is represented as 2, 1 with the new basis vector b prime, okay, and then this b prime has the first basis vector of 3, 1 and the second basis vector is negative 2, 1, right? And then now let's think of linear transformation of this guy. Okay, so that is correspond. So this is b1 and b2, and let's think of this b1. Okay, and then suppose this guy is 4, 5, or maybe 3-dimensional vector 4, 5, 6. Okay, and then now let's represent this guy as the new coordinate vector C, and that is represented as maybe 7, 8 with respect to C, where C is maybe 1, 2, 3 and 2, 3, 4. Okay, so this guy is represented as T of B1 with respect to C. Okay, so that is 7 and 8. Okay, so So that is this part. And R1 through Rn is the original linear combination coefficient to represent the input vector x in terms of the basis vector b1 through bn. Okay. So this guy, where we represent the b coordinate vector into, transformed into the c coordinate vector in the output, and we can think of their transformation such as d, for example. Okay, so this d is now represented as this new matrix M. Okay, new matrix M, and that is formed as this form. Giving the input as B1 and then linearly transform them using the same linear transformation matrix T, and then representing it into the C coordinate vector, and so on, right? Okay, and then that is our new linear transformation matrix. And then what should be the input over here? This input should be the B coordinate vector. With respect to the new basis vector B representing the domain. Okay? So it's a little bit non-intuitive or a little bit confusing, but yeah. But if you keep this kind of special case in mind over here, so in this case, although it is a special case, but we now represent the input vector and output vector with respect to our eigenbasis. Okay, and then the corresponding coordinate vector for input and output and their linear transformation. Okay, so that is D over here. Okay, so D is just a diagonal matrix, and so here this D, when 2, 1 times -2, I'm just rewriting it, and then it is -2 and 2. Okay, so this is what? This is an input vector represented as this B, right? So that way we obtain 2, 1, and this is what? This is output vector, right? Which is originally like this -10, 0, but this guy is represented still as with respect to the basis vector B, right? So this is the output coordinate with respect to the basis B, right? And here this guy is our D, right? So this is like the over here, so this new matrix M over here, and input is represented as a B coordinate and the output is represented as a C coordinate, but in the case of an eigendecomposition and the linear transformation using the eigendecomposition form, C and B are the same one. Okay, so that way it's a special case of this guy. Any questions? Right. And then we can think of this general form. So x and tx is represented in terms of the standard basis in the domain and the codomain. But here we represent it as a new with the new basis vector B and the output as the new basis vector C, and we can also define a new matrix multiplication or new linear transformation, defined on this input and output vectors, defined, represented in the new basis vector B and C. Right. Then let's look at this example. So B is this guy and C is this guy. So these work as a basis vector for domain, and these guys will work as a kind of codomain. Right, and then B is represented in this form, and B1 and B2 is represented in this form. And what is M over here? That takes the input as the coordinate vector with respect to the basis B and gives an output of the coordinate vector with respect to the basis C. Okay? So in this case, when taking the B1 as an input, and then 3, -2, and 5 will be the coordinate. I mean, this is an output, and what is the coordinate of this output vector with respect to our basis vector C, or C1, C2, and C3? So that is simply 3, -2, 5, right? And then B2 is represented into this form, I mean after transformation, and then 4, 7, -1. So this guy is our M. So it will take the input, which is represented as this B coordinate, and then what is the output? The three-dimensional coordinate vectors will be linear combination coefficient assigned to our basis in the output domain, or C1, C2, and C3. Okay. Okay, then yep, so we consider this a special case of our input and the domain and the codomain has the same dimension, or our matrix T is represented as an AX, where A is a square matrix. So that way the input and output dimensions, or the domain and the codomain, has the same dimensions. And given this the same dimensional space, and then now let's think of the B and C are actually the same basis. Okay, so this is the situation that we handled over here, and input and output will be represented with respect to the basis vector of eigenvectors, right? Okay, so over here, so our M is our eigenvalue diagonal matrix whose diagonal entry is eigenvalues, right? And then let's look at this case. So this is a domain, and the codomain is not R2, but it's a P2. So this is the entire set of a second order polynomial. Something like ax squared and bx plus c. Okay, so we consider the entire, all the possible second order polynomials in this form, and that is our domain and the codomain. Okay, so even before thinking of any kind of dimensionality and so on, so this is an arbitrary input polynomial, right? And this is output polynomial. So this is our function definition. Okay, and this is actually, by the way, this is a derivative operator. Right? If we take the derivative, and then it's 2a2t a1, and that's it. 네, 미분이죠? differentiation operator, right? Okay, so let's think of, seemingly this guy doesn't have any kind of vector form at all. So this is just a single polynomial, right? But here, let's also think of the basis that will represent any arbitrary second order polynomial in our domain, and the basis can be 1t and t plus 1. Okay, and then given this basis, this ax squared and bx plus c, and let's represent this them as a b coordinates, and then it will be 1 and t squared, right? So t squared and t sorry. So this is the first basis, and so the coordinate is, yeah, so let's use this guy. So in this case, so 1 and its the corresponding linear combination coefficient is A0 and A1 and A2. Right? So this is the coordinate vector with respect to this basis of this polynomial. Right, and then yeah, now let's think of the linear transformation matrix T that takes the input as the some b coordinate. I mean the coordinate with respect to this basis of like 1t and t squared. Right, and then let's think of this linear transformation matrix A over here. And then the result is also the b coordinate vector with respect to this guy. Okay? And then now, how can we form this matrix A, or maybe M that we denoted over here? Okay? So, how can we form A? We simply fill out those columns. Okay? Columns as like, yeah, so the first column will be T of what? 1, 0, 0. So this is B coordinate, right? So this is an A0, just simply the constant, right? So yeah, differentiating this constant, okay? And then it will become 0, right? It says 1, 0, 0, and that will be just simply 0. And thus, yeah, what is the linear combination coefficient that will form this 0 with respect to this basis? It will be simply 0, 0, 0, 0, right? And so this guy, yeah, this guy representing it is this new coordinate vector B is simply 0, 0, 0. So that will be the first column of a matrix A, right? So what about the second column? Second column is like we take the input of this guy, and this guy is simply T, right? Because we just assign 1 as a linear combination coefficient to the second vector in our basis vector B, right? But all zeros for all the other basis vectors, right? And so in the case of T, or here 0, 1, 0 over here. Okay, so in this case, it will be 1 and 0. And in this case, how can we represent it with respect to the basis vector B over here? That will be 1, 0, 0, right? Because this times 1, this times t, this times t plus 1, and add them together, and then there will be this output. Okay, so again, in this input representation, we just use the b coordinate as 0, 1, 0, which corresponds to just t, right? And in this case, if we just plug in a0, a1, and a2 over here, and then we just obtain 1 times nothing, I mean 1 plus, and a2 is 0. Okay, so this 1, yeah, simply just 1, and 1 is represented as 1, 0, 0 with respect to the basis vector of 1t and t squared. Okay, right, and then this was the output of B1, and the second, I mean 0, 1, 0 is the output of B2. Okay, and then what is the output of a B3? B3 is 0, 0, 1 over here, and so over here it is 2. It becomes 2, right? And so the output vector will be 0. Oh, sorry. 네, 이거 잘못했죠? 1, 0, 0. Great. Right? 0, 2, 0. Right? Because we have over here, we have an output of 2t, right? And so with respect to the basis of 1t and t squared, and then the linear combination coefficient of 2t is 0, 2, 0. Right, and so our matrix M will be 0, 0, 0, 1, 0, 0, and 0, 2, 0. Okay. Right, so that is our matrix T, where the input is the B coordinate and the output is also the B coordinate. I mean the basis by using the same basis vector B in both of the input and output. Okay, so back to this theorem, and that is called the B matrix. Okay, the linear transformation matrix, or the maybe standard matrix, where the input is represented as with respect to the B basis of B, and also output is represented as the same basis vector B. Okay, in that case, input and output are B coordinate vectors. In that case, the linear transformation matrix is called this B matrix. And so we just obtained this B matrix over here, and that is represented as this form. Okay. And then now, for a general kind of P of T, then this guy is a general input polynomial, and then its linear transformation is this guy, and then this guy is directly represented as the linear transformation of this 1 and t plus squared, and then their coordinate is a1 corresponding to the constant term, 2a2 is corresponding to the t, and 0 corresponding to the t squared. Okay, so that is represented in this form. Okay, right. So that is represented as, this is our B matrix that we already obtained in this example. Okay, so that is, so given the arbitrary input polynomial and their corresponding coordinate vector with respect to 1t and t plus 1 as our basis will be represented in this form. And so once multiplying like a and maybe this guy, and then this result is the same as the output result that we originally are given as this output form, right? So we just verified, by forming this B matrix in this form will be actually equivalent to our original function definition over here, right? And time's up. So that's it for today. And we will continue this chapter in the next class, and then move to the chapter 7, which is the probably the most important part. Okay, thanks.
그래서 그냥